Good day. This is Mikhael Camarillo, and my partner is Omar Tolentino, and our topic is Introduction to Electronics Communication. So, what is communication? Does imparting knowledge or transferring data is a type of communication, or does successfully conveying or imparting ideas and feelings to the others is also a type of communication? In the next slide, we can see the definition of communication. Communication is defined as the basic process of exchanging information. It is an act of conveying meanings from one entity or group to another through the use of mutual understood symbols, signs, and semiotic rules. It is a process by which information is exchanged between individuals through a common system of words, symbols, signs, and or behavior. The next slide is about communication barriers. There are two types of communication barriers, which is language and distance. There are many reasons why communication may fail. In many communications, the message or what is being said may not be received exactly the way the sender intended it to be. It is therefore important that the communicator seeks feedback to check their message is clearly understood by the receiver. The language barrier is when two races speak to each other, having two different languages, and they couldn't understand each other. But now, in our current technology, we have an AI in our mobile application which could translate what the speaker says. And the other is the distance, where the communication is far away from its receiver and there would be no communication occurred. Communication is very important in our lives. And the next slide is about the evolution of communication. At the first phase of communication, symbols, carrier pigeons, smoke signals, and cave paintings. The second phase of communication is postal system, newspaper, radio, television, telephone, telegram, Morse codes, and fax machines. And in our present time, we have this kind of communication, which is internet, email, text messages, cellular calls, and social media. The next slide is about timeline of milestone in human and electronic communication. The first is Professor Joseph Henry. In 1830, Professor Joseph Henry transmitted the first practical electrical signal. He built the world's most powerful electromagnetics. In 1837, Samuel Morse invented the telegraph. The telegraph revolutionized the long-distance communication. He also invented Morse code. In 1876, Alexander Graham Bell invented the telephone. He was awarded the first U.S. patent for the invention. With the help of Thomas A. Watson, in 1887, in November 1886, Heinrich Hertz became the first to transmit and receive radio waves. In 1887, Guglielmo Marconi developed first apparatus for long-distance radio communication. He was first to discover and demonstrate wireless radio wave propagation. In 1901, he accomplished the first transatlantic transmissions of radio signals. In 1903, John Fleming is renowned as the father of electronics. His two-electrode vacuum tube rectifier, or diode, was used for so many years before the invention of modern transistors. In 1906, Lee DeForest invented the Odeon, or the triode vacuum tube. Triode was the first practical amplifier device. In 1923, Vladimir Zworykin invented and demonstrated the television. He invented a television transmitting and receiving system employing cathode ray tubes. 1948, the transistor was successfully demonstrated in December 23, 1897 at Bell Laboratories in Murray Hill, in New Jersey. The three inventors are William Shockley, John Bardeen, and Brattain. In 1959, the first integrated circuit was invented by Jack Kilby of Texas Instruments. In 1965, the early bird World's first commercial satellite was launched on April 6, 1965 by Communications Satellite Corporation or ComSat. And 1983, the cellular phone network was first introduced by Ameritech Mobile Communications or AT&T in Chicago, Illinois. The next slide is about the summarization of the milestones. In the year 1830, Professor John Henry transmitted the first practical electrical signal. 1837, Samuel Morse invented the telegraph. 1876, Alexander Graham Bell and Thomas A. Watson invented the telephone. And Guglielmo Marconi demonstrated wireless radio wave propagation. 1901, Guglielmo Marconi accomplished the first transatlantic transmission of radio signals. 1903, John Fleming invented two-electrode vacuum tube rectifier, or which is the diode. In 1906, Lee DeForest invented the triode vacuum tube. In the year 1923, Vladimir Zworykin invented and demonstrated television. 1948, William Shockley, Walter Brattain, and John Bardeen invented the transistor. 1959, integrated circuit was invented. 1965, the first communication satellite was launched, and 1983, the cellular telephone network was first introduced in the United States. The next topic is about electromagnetic spectrum. What is electromagnetic spectrum? Electromagnetic frequency spectrum refers to the entire range of usable frequencies. It extends from a few hertz to cosmic rays. So, what is frequency? Frequency is the number of complete cycles that alternating does in 1 second. Here is an example of a frequency. This graph is an alternating current. As you can see in the graph, there is more than one cycle in the graph. One cycle is about 0.25 seconds. As you can see here, that is one cycle. And the second cycle is 0.5 seconds, and so forth. And this graph is made of 4 cycles per second, or 4 hertz. And the other graph is 14 hertz. Federal Communication Commission band designations. This is the table of different frequency ranges. Extremely low frequencies. Frequency range of 30 to 300 hertz. AC power line frequency is an example of it. As you can see, 50 hertz is about, it uses 220 volts to 240 volts, and the 60 hertz uses 110 volts to 127 volts, as well as the low end of hearing, which is the 20 hertz. The next is voice frequencies. Frequency of about 300 to 3000 hertz. It is also known as voice band. This is the normal voice, although it extends from 20 to 20 kHz. Most intelligible sounds occur in this range. The next is the very low frequencies. The frequency is about 3 to 30 kHz. It includes the high end of human hearing, which is 20 kHz. It also includes some instruments, which could exceed about 20 kilohertz. Also, very low frequency have large wavelengths that allows them to diffract large obstacles, propagate as the ground base along the Earth's curvature, and penetrate the salt water. That's why military use it for communicating in submarines. The next is low frequencies. About the range of 30 to 300 kilohertz. This frequency is primarily used in aeronautical communication, as you can see in the example, and marine navigation, so as its wavelengths range from 1 to 10 kilometers, also known as kilometer wave. The next is the medium frequency, about 300 to 3000 kilohertz. And major application of this is AM radio, which is 535 to 1605 kilohertz of usage. The next is high frequency, which is the range is 3 to 30 megahertz. Generally known as short waves. Example is a two-way radio communication. Communication of this frequency is called shortwave radio. Also, the radio waves of this band can be reflected back to Earth by ionosphere layer in the atmosphere. This method is called skip or skywave propagation. The next is very high frequency. The frequency range is 30 to 300 megahertz. The common uses of very high frequency are radio waves, digital audio broadcasting, FM radio broadcasting, television broadcasting, and marine communications. Next is high frequency. The frequency range is about 300 to 3000 megahertz. This frequency can be blocked by hills, although the transmission through building walls is strong enough for interception. So they are used in television broadcasting, smartphones, satellite communication, including GPS, personal radio services, Wi-Fi and Bluetooth, and other more. The next is super high frequency. The frequency range is about 3 to 30 gigahertz. It is mainly used for satellite and radar communications. These frequencies fall within the microwave waves. Radio waves with these frequencies are called microwaves. So this is used for most radar transmitters, wireless LANs, and more. They are also used for medical diathermy, microwave hyperthermy, or to cook foods in microwave ovens. The next is extremely high frequency, which is about 30 to 300 gigahertz. So its waves can carry enormous amount of data and find wide application in radar. It is used for civil terrestrial communications and satellite communications. The next is infrared. The infrared frequency ranges from 300 gigahertz to 400 terahertz. Infrared lights are invisible to human eye. Although longer infrared waves can be sensed as heat, it also used in anatomy to detect stars or remote control units, guidance of weapon systems, and optical devices. The next is visible spectrum. About frequency ranges about from 0.3 to 3 petahertz. It is a portion of electromagnetic spectrum that is invisible to human eye. So electromagnetic radiation in this range of wavelength is called visible light or light. Light with colors, except with violet and pink, because it has to have a mixture of lights or wavelengths. And the next is ultraviolet. The frequency ranges from 3 to 30 petahertz. The ultraviolet rays can be used to kill microbes. Hospitals use UV lights to sterilize surgical equipment. This can also help the body to produce vitamin D. There is a machine that is used by doctors to cure vitamin D deficiency or some skin disorders. The next is X-rays. The frequency ranges from 30 to 300 petahertz. The most familiar use of X-rays is about some broken bones or to see the teeth build up for the doctors easily can cure or remove the bone. The next is gamma rays. The frequency range is about 0.3 to 3 exahertz, used in medicine, specifically in radiotherapy, and the industry's sterilization and disinfection. The nuclear industry. And the last one is cosmic rays, about 3 to 30 exahertz. It is now being studied to predict geomagnetic storms, big increases of radiation hazards, and other dangerous phenomena in space and on the Earth for people technology. So the last topic would be the wavelength. The length that one cycle of electromagnetic wave occupies in space, also the distance between similar points in repetitive wave. Here is the formula. This lambda equals k times c over f. The k is the velocity factor, or equal to 1 in free space. The c is velocity of light in free space, about 3 times 10 raised to the 8 ms, and f is for the frequency. And the next topic would be introduced by my partner, Omar Tolentino. Thank you for listening.
Hi guys, my name is Omar Tolentino, and for this part of our report, I will be discussing bandwidth and information capacity. So, in the electronics communication system, there are two known limitations. One of them is noise limitation, and the other one is the bandwidth limitation. Okay, so first let's talk about the first limitation, which is noise. Noise may be defined as an unwanted form of energy which tend to interfere with the transmission and reception of desired signals in a communication system. This noise cannot be eliminated completely. However, the effect of noise on desired signal can be minimized with the help of several techniques. Noise can be classified into two categories depending upon the source. As you can see in the picture, those two categories are external noise and internal noise. External noise is a type of noise whose sources are external to a communication system, while an internal noise is a type of noise whose sources are internal to a communication system. On the second limitation is bandwidth. So what is bandwidth? Bandwidth is the frequency range or the band of frequency needed for a particular given transmission. This is always allocated by some international regulatory agencies because it is essential to avoid interference among the signals having the same frequency. The information theory, which is used in bandwidth, states that the greater is the transmission bandwidth of a communication system, the more is the information can be transmitted. In bandwidth, the relationship of the bandwidth basically is the difference between the upper and the lower frequency limit, as you can see in this equation below, where bandwidth is denoted as BW. So now let's talk about the equipment limitation. Okay, the noise and bandwidth limitation dictate theoretically what can or cannot be achieved in terms of performance in a communication system. However, this theoretical limit may not be realized in a practical system due to equipment limitations. We also have other terms like information capacity and Hartley's law. Okay, so what is information capacity? Information capacity is a measure of how much source information can be carried through the system in a given period of time, whereas Hartley's law, if you would remember some of the topics that you might have covered prior to this subject, like Electronics 3, states that the information capacity is directly proportional to the bandwidth and the transmission line. Okay? And as you can see on the equation illustrated below, we can see the relationship between the information capacity, Hartley's law, or rather, the information capacity and bandwidth and then time. So now that we have discussed those concepts, let's now move to signal analysis. So in signal analysis, there are different factors that affect the signal. Okay? The first one is distortion. Distortion is a signal alteration due to the imperfect response of the system to the desired signal. Whereas interference is the contamination of extraneous signal, usually man-made, to a form of similar to the desirable signal. While noise is a random, undesirable high-frequency spike, while the attenuation is the decrease in signal level. In signal analysis, there are two types of signals. They are baseband signal and demodulated signal. So first of all, what is the baseband signal? The baseband signal, also known as the low-pass signal, is a signal that can include frequencies that are very near zero by comparison with its highest frequency. Baseband signal can be seen on your upper right-hand side of your screen. We can see here the relationship or the characteristic of the baseband signal with respect to frequency. Okay. Another type of signal is the modulated signal. Modulated signal undergoes a process called modulation. So modulation is the process of imposing an input signal into a carrier wave. Okay? So, in other words, modulation changes the shape of a carrier wave to somehow encode the speech or data information that we are interested in carrying. So, to keep it short or simple, modulation is like hiding a code inside the carrier wave. And we can see that in the lower hand side of your screen, the characteristics of a modulated signal. In signal analysis, once again, the transmission of information also needs transmission facilities, and there are two schemes for the type of transmission. One of them is analog and another one is digital. Analog systems are an integral part of most INS digits, and encoded symbols generally retain their digital identity through these analog systems. Whereas digital system is a system which deals with discrete signal. The input and output of the system is two binary value, which is 0 and 1. Okay, so what you can see here, okay, the illustrated figure here is the analog signal and the digital signal. Okay, so we can also see the difference between what an analog signal looks like and then what a digital signal looks like. So there are actually advantages and disadvantages of digital over analog, or pros and cons. Okay, the advantage of digital over analog is that, first of all, it's easy to multiplex. Another one is that it improved noise immunity. Number 3, it is better, it has a better performance, and lastly, it is easier to interface than analog. Okay? However, the disadvantage of using digital over analog is that there is a need for large bandwidth. There is a need for synchronization, and there is a need for additional equipment. And you are mostly restricted to a wired topology. So if you're an engineer, you should expect to spend more money or to spend more resources in using analog as compared to using analog. So in signal analysis, once again, there are kinds of signal representations. The first one is the time domain, and the other one is the frequency domain. Time domain is basically amplitude versus time, as you can see here. Okay? And the other one is the frequency domain, which is the amplitude versus the frequency, which also you can see here. The difference between these two signal representations is that a time domain graph shows how a signal changes over time, whereas a frequency domain graph shows how much of the signal lies within each given frequency band over a range of frequencies. There are also several classification of signals in signal analysis. Okay? The first one is the classification according to period. Periodic signals, okay, in this classification are signals that keep on repeating at a regular interval, like a sine wave. Okay? And the other one is a non-periodic signal, where signals that keep on changing continuously and has no definite period. Okay? And there is also classification according to a form of electrical signal. Okay? And for that, we have sinusoidal signals, which has the formula illustrated here. Okay? And then a non-sinusoidal signal, where it is the sum of series of the sinusoidal. And lastly, there is also classification according to symmetry. Okay? The first one is even symmetry. Even symmetry occurs when a periodic waveform is symmetrical about the vertical amplitude or axis. Okay? And that relationship is stated here, where f of t is equals to the f of negative t. Okay? The second one is the odd symmetry, where a periodic waveform that is symmetrical about a line midway between the vertical and the negative horizontal axis, where f of t is equals to the negative f of negative t. And lastly is the half-wave symmetry. It is a periodic waveform that for the first half cycle repeats itself with the opposite sign for the second half cycle. I don't know, guys, if you can see the relationship of the half-wave symmetry, but essentially a half-wave symmetry, the relationship of the half-wave symmetry is f of t equal to f of t over 2 plus t. So now that we have discussed that topic, let's now move into electronic communication systems. But first, let's ask ourselves, what is electronic communication systems? So, a communication system. Let's talk about a communication system first. Okay? A communication system is a system model that describes a communication exchanges between two stations, transmitter and receiver. Okay? Signals or informations passes from source to destination through what is called channel, which represents a way that signal use it to move from source toward destination. Okay? So in a communication system, we basically have a sender, a channel, and a receiver. Okay? So a good example of this communication system is actually what we are doing today. Okay? Where as a speaker, I am the sender, and my stable internet connection is the channel, where you guys and our professor are the receiver. Okay? But to keep it more technical, to be more detailed on what a communication system is like, a basic elements of a communication system are the transmitter, the receiver, and between them is a communication channel. So, this is the block diagram of a communication system. Okay? So, let's check or let's discuss the parts of this block diagram of this communication system. Okay, so the first part is the input transducer. Okay, an input transducer takes a form of physical energy and converts it into a signal which can be read. Okay, for example, a microphone. Okay, a microphone takes physical sound waves and turns them into electrical signal which can be transferred through wires to the amplifier. Okay, the second one is the transmitter. A transmitter is an electronic device used in communication to produce waves in order to transmit or send data. Whereas a channel, as discussed before, refers to a physical transmission medium like wires or logical connection over a multiplexed medium like a radio channel. Okay? And what is a receiver? Okay? Receiver basically, from the name itself, accepts signals like radio waves and convert them frequently with amplification into a useful form, while the output transducer converts the electrical signal into a non-electrical signal like a sound signal, light signal, or both sound and light, which could be then given to who is listening or to who is going to be the recipient of that message or that signal. Okay, so now let's move on to transmission modes. Okay, so what is a transmission mode? Transmission mode is also known as electronic communication mode. Okay, it is a means of transferring of data between two devices. Okay, and between those two communication devices, transmission mode also defines the direction of the flow of information. Okay, and for that to happen, we need communication devices. Okay, what is a communication device? A communication device is any type of hardware capable of transmitting data, instructions, and information between a sending device and a receiving device. The following types of communications devices are dial-up modems, different types of modems like ISDN and DSL, cables, wireless modems, network cards, wireless access points, and routers. So what is ISDN and DSL modems? For those who do not know, an ISDN modem sends digital data and information from a computer to what they call an ISDN line and receives data and information from an ISDN line, whereas a DSL modem sends digital data and information from a computer to a DSL line and receives the digital data and information from a DSL line. In transmission mode, there are 4 types of transmission mode, okay? And they are the simplex, half duplex, full duplex, and full/full duplex or F/FDX. In simplex, okay, simplex has no mechanism for information to be transmitted back to the sender. Okay? This type is also called one-way communication. And since it is one-way communication, the communication is unidirectional. Okay? Only one of the two devices on a link can transmit and the other can only receive. Simplex circuits are analogous to escalators, doorbells, fire alarms, and security systems. Okay? Other examples also include like computer monitors and keyboards and keypads. Another form is called half duplex or HDX. They are called the two-way communication. In HDX, each devices or each station can both transmit and receive, okay, but not at the same time. Okay, both sender and receiver can send and receive the information, but only one is allowed to send at any given time. Okay, a perfect example of this is a radio, or what we would call a walkie-talkie. Okay, if I am a person calling someone on a walkie-talkie, okay, I can only contact him or call him if he is not calling me at the same time. Okay, if I am calling that person and he's not calling me at the same time, we can establish a communication where I am going to send him something through voice and he will listen and he can hear what I'm saying on the other end. And that's how HDX simply functions. Another type is also called the full duplex or FDX. Okay, in FDX, the communication between sender and receiver can occur at the same time, unlike HDX. Okay? In FDX, both devices or stations can send and receive data at the same time. Signals going in one direction share the capacity of the link with signals going in other direction. Okay? And this sharing can occur in two ways. Therefore, in this mode, transmissions are possible in both directions simultaneously, but they must be between the same two stations. Okay? And for your further information, full duplex lines are also called two-way simultaneous, duplex, or pathway lines. So for a simple understanding of what we have discussed a while ago, I've made a chart, okay, between these three types of mode, like simplex, half duplex, and full duplex, on the basis of direction of communication, sending and receiving, performance, and example. Okay? What we notice in simplex or SX is that the direction is unidirectional. Okay? And since, once again, it is unidirectional, it can only send data. Senders can only send data. And receivers can only receive data. Okay? However, it is noted that between the three, it is the worst performing mode of transmission. Okay? Because unlike the full and the half duplex, okay, receivers, cannot send data as well. Okay? So that's why it's actually the worst performing mode of transmission. Okay? So now let's move to the half duplex or HDX. Okay? Just like the full duplex, the direction of communication of HDX and FDX is two-directional. However, the difference between HDX and FDX is that it is in HDX, okay, the direction of communication might be two-directional, but it can only occur one at a time. Whereas in FDX, the direction of communication is two-directional, but it can occur at the same time. It could be simultaneous. Okay? In sending or receiving data, in HDX, senders can send and receive data, but since it's one at a time, it can only happen one at a time. Okay? And same thing goes to FDX. Okay? In terms of performance, okay, in comparison to these three types of modes, HDX is better than simplex. However, it is noted that since the direction of communication is simultaneous in FDX, it is better performing than the rest of the other modes in this table. But we forgot another mode of transmission, also called full/full duplex or F/FDX. In F/FDX, okay, it transmits and receives simultaneously but does not necessarily between the same two locations. In F/FDX, in this mode, transmission is possible in both directions at the same time but not between the same two stations. Like, one station is transmitting to a second station and receiving from a third station at the third time. Full/full duplex is possible only on multi-point circuits. Okay, so now that we have discussed transmission modes and other concepts related to that, we now move to transmitters. So, what is a transmitter? What is a transmitter? A transmitter is a collection of electronic components and circuits designed to convert the information into a form suitable for transmission over a given communications medium. The components of a transmitter are the following, as illustrated in the figure below. It has the amplifier, modulator, the oscillator, and the antenna. Okay? But for a communication to happen, obviously, we need communications channel or medium. So what is a communications channel? Okay? A communications channel provides the means of transporting signals between a transmitter and a receiver. The two general types of communications media are one, guided, and the other one is unguided. The difference between guided and unguided is that in guided, it is wired, whereas in unguided, it is wireless. Okay, an example of guided media are like, coaxial cable, fiber optic cables, and waveguide, whereas the examples of unguided media or wireless media are radio waves, lasers, and Bluetooth. Okay, aside from transmitters, we also have receivers. Receivers are a collection of circuits or electronic devices that accept the transmitted message, form the channel, and convert them into a form understandable to humans. Okay? The components used in a transmitter, okay, are somewhat used also in a receiver. Okay? The components of a receiver are the amplifiers, tuner, detector, and antenna. Okay? So, to explain the parts of these receivers, okay, an amplifier is a device that takes an audio signal and amplifies it so that your speakers can use it to play the audio. Okay? The next part is the tuner. Okay? A tuner is a subsystem that receives radio frequency or any type of frequency transmissions and converts the selected carrier frequency and its associated bandwidth into a fixed frequency, which is suitable for further processing. Okay? It is also mentioned that receivers use a detector. So what is a detector? A detector is a device or circuit that extracts information from a modulated radio frequency current or voltage. And lastly, antenna. Receivers, just like transmitters, use an antenna. So what is an antenna? Okay, so for those who do not know, an antenna converts some of the energy from the incoming radio waves into tiny radio frequency, AC voltage, which is applied to the receiver's input. Okay? And that's all for my part in this report. Thank you very much for watching. I hope you learned a lot through our discussions. And once again, thank you very much for watching and stay safe.